The catalogue pavement design will highlight the philosophy of residential street design, the structural design of the street pavement, the importance of the level of service by users, some maintenance aspects, and the comparison of proposed pavement designs on a life cycle cost basis. The catalogue method is referenced from the Red Book Chapter 8. The method will discuss selected elements with particular emphasis on the design period, bearing capacity, subgrade, and selection of a final pavement design based upon cost. The overall design philosophy, design approach, and design procedures presented in this chapter are applicable to urban streets in South Africa. Design question 1 from the design book will be used as the example in this presentation. You are required to identify all possible pavement structures and cost them. The final design is to be presented with a minimum compaction. Please note that the text presented in red are changes which have been affected to the question. Update your question accordingly. In this calculation you are provided with a location, some description of the pavement, the time when it will be opened for use, subgrade information, granular and hot mix fill spaces are to be considered when looking at the catalogues, a growth rate of 6%, and axle count data to calculate your traffic. You're also provided with material costs. Characteristics which define the profile of the street include a description and function of the street, vehicle traffic, and design bearing capacity. Street categories range from arterial streets to access streets. Arterial streets being class A and B, and access streets being C and D. D is further divided into streets which carry more and less than 75 vehicles a day. Streets which carry more than 75 vehicles a day require a sturdier design. Arterial streets carry a heavier load, thus their loads are justified. All attempts should be made to pave arterials carrying bus and heavy good vehicles to suitable, relatively low risk pavement standard. Where there are financial constraints, the street network should then be prioritized on an economic basis to identify candidate streets for upgrading, also known as a pavement management system. Normally, a design strategy is applicable only to paved category A and B streets. The analysis period is a convenient planning period during which complete reconstruction of the pavement is undesirable. The structural design period, on the other hand, is defined as the period for which it is predicted with a high degree of confidence that no structural maintenance will be required. In order to fulfill the design objective of selecting the optimal pavement in terms of present worth of cost, it is necessary to consider how the pavement is expected to perform over the entire analysis period. The manner in which design strategy can be presented is demonstrated in the two ways presented on screen. Over time, the riding quality decreases. Design 1 requires resealing to maintain the surface in good condition, and later on might require structural rehabilitation, preferably after 20 years. Higher order Class C, Class B and A are typical of this design. Design 2, which is structurally adequate for the whole of the analysis period, note analysis and structural are similar, requires only 3 resealings, 1, 2, 3. Resealings are typically done between 5 and 7 year spans. This is typical of lower order class roads like a D and a low order C. The analysis period is realistic. There may be a difference between the analysis period and the total period over which a facility will be used. The analysis period is often related to the geometric life. If the street alignment is fixed, a period of 30 years will be used. To grapple with the PWOC, or present worth of cost, we understand it to be the current value of building the structure. However, after 1 year, maintenance comes into effect, and by year 2, maintenance is an escalating cost. Thus, in year 0, we only consider the construction costs. In year 1, we add a maintenance cost, and in year 2, we escalate the maintenance cost. Thus, design 1, the costs are typically higher due to better material, multiple maintenance treatments, and a more expensive structural rehabilitation cost, far outnumbering possibly the cost of design 2. As mentioned earlier, Class A and B category analysis period is 30 years. However, for category B, it can only retain a 20-year STP, structural design period, if the alignment is fixed and there are no huge concerns. However, where there is a lack of confidence or financial problems, etc., that analysis period then can be reduced to 15 years. And similarly, the longer analysis period can be reduced to 25 years rather than 30 years. So, to repeat, the AP and the STP can reduce from 30 and 20 respectively down to 25 and 15 if there are strong concerns around finance or a lack of confidence, etc. Category D streets are not considered for a structural design period. Pavements are designed for a number of standard 80 kN axles. The total number of standard axles that a pavement structure will be able to carry over its design life is referred to as the bearing capacity of the pavement. This table summarizes the bearing capacity interval known as pavement classes. The cumulative equivalent traffic can be determined by estimating from tabulated traffic classes, but it can also be estimated or calculated through a detailed calculation from daily traffic axle loads, growth rates, and lane distribution factors. Now, the detailed computation is illuminated somewhat here. There are two factors which are considered for growth rate, and the average daily traffic can be given or can be calculated from an axle counter. The lane factor is typically given as 1 for educational purposes. The load equivalency factor relates to the number of repetitions of a given axle load to the equivalent number of E80s. Equivalent traffic can be determined by multiplying the number of axle loads in each load group in the entire load spectrum by the relevant equivalency factor. This equivalency factor is a function of pavement composition, material types, definition of terminal conditions, and street reliability. The cumulative equivalent traffic bearing capacity over the structural design period of 20 years may be calculated in 3 steps. By determining a growth factor for future traffic from initial traffic. Table 8.8 demonstrates a 3-year period to opening of the road and a 6% growth rate. The next step is by selecting excuse me, a lane factor, which for our scope of work will always be 1. And finally, by selecting a compound growth rate. In this example, our structural design period is 20 years. Our growth factor is 6%, therefore our number is 14,232. Where the growth rate is an uneven number such as 3, 5 or 7%, we would take the two even numbers and average them off to get our answer. Where growth rate is not given, students may use 6%. So this would typically be how the calculation should be laid out. Cumulative daily traffic multiplied by our 3 factors to give an answer of 6.9 million axles. It's preferred that the format is written as times 10 to the 6 or times 10 to the 4, as it just becomes easier than to read the catalogues.
This table is revisited to confirm the traffic class is an ES10 due to the bearing capacity of almost 7 million E80s. However, should the pavement class have changed between the various growth rates, for example, from an ES3 to an ES10, then the selected pavement class would have been necessitated motivation. In the example provided, the design load at 6% is too low to select an ES10, as growth is not guaranteed to be achieved. So, if the expected growth was 7% instead of 6%, then it would provide a stronger case for an ES10.
CBR values would be determined, for example, with a DCP test and the like. For contextual purposes, this information will be issued to the student. The minimum requirements for a subgrade is CBR of 3 in dry conditions. In wet areas, a minimum soak CBR of 3 would be required. Values of less than 3 would need to be treated. Just to repeat, the student would be issued with the subgrade information, and also we would work with an assumption that the subgrade would be the same, consistent for the entire length of the study area. Subgrade areas are delineated before construction as per table 8.12. Subgrades with a CBR of less than 3 would require treatments such as chemical or mechanical stabilization, chemical modification, or the removal or addition of extra cover. Therefore, it will be classified to a group. For this design context, we elect the same subgrade group for all design areas of the road. See table 8.19 for subgrade layers. The higher the value of the CBR, little or no subgrade would be required. Thus, after we select our catalog design, we are going to add our selected layers, and we will, when necessary, rip and recompact the subgrade, the in situ subgrade, or if necessary, we will stabilize it to reflect a acceptable CBR. Some of the designs catalogs are based upon mechanistic, empirical design, as well as the DCP method, as well as a few pavements from field experience. Using the road classification, bearing capacity, and climate information, we are able to select appropriate catalogs. The design question will limit the number of catalogs selected. So just to highlight, when we're looking at granular bases, we've got to separate our dry/moderate from wet conditions. Similarly for block pavers, etc. In this example, the two catalogs we narrowed down are granular and asphalt, because in our question we are directed to only look at granular and asphalt mixes. Also, we are guided by the load of the pavement towards identifying the traffic class, which is an ES10. Most materials are priced per cubic meter. However, materials are quantified per meter squared when placed into a schedule of quantities. The cost calculation is standardized accordingly. As per the earlier assumption that the subgrade CBR is consistent throughout, the same selected layers is added to any of the selected designs. HMA in particular requires a tag code. Most other catalogs would only require a prime code. Within the course design context, the cheapest catalog is chosen based on the present material cost only. For the purpose of our design calculations, no other criteria will be considered. However, in a project environment, we call it value added and ask the student to evaluate additional criteria. Please note that the present worth of cost is only established in the present year where the maintenance is 0. However, should the cost be considered for the analysis period, the maintenance and rehabilitation would have to be considered as well as escalation thereon. If we are evaluating different catalogs and we're putting the same wearing course down, then the most critical layers really become the base course and the subgrade base, because remember, we are assuming the same subgrade for each and every design. So where we are putting down, for example, a 40mm asphalt layer, all of those catalogs will have the same wearing course and the same subgrade. So the price comes down to the base and the sub-base. So when you're costing, this is really where you need to cost in our design context. You make your final selection and then you add your subgrade for a final price. Material property strength is strongly dependent on the compaction achieved in the field. The minimum compaction standards are presented in Table 8.14. It is important for this design to be acknowledged in the calculation context. Over the next 3 slides, you are presented with a desirable layout for your calculation. We will start with identifying road category, analysis period, structural design period. Then we will compute the cumulative daily traffic, known as E80s, and then proceed to calculate the design load or bearing capacity for the analysis period of the pavement. We then identify traffic class, climatic region, our subgrade conditions, and finally, we identify all the applicable catalogs as per the scope of the question, and we price, we make a final selection, and that final selection, we add on the subgrade pricing and the compaction, and also it would be nice to then calculate the final quantities of the pavement. And the final quantities of the pavement is typically in meters cubed. We're given the area of the pavement, length by breadth, and here we have the depth, so it's a simple length by breadth by depth to get final meter cube quantities of the pavement layers. Thank you very much for joining me. Most appreciated, and I look forward to seeing you in the next video. Bye-bye.